So let us look into one more approach which would be widely used when we will go to some deep learning algorithms. But I think that linear regression is a good opportunity to develop some visualization for this approach, what we call as gradient descent approach. So as the name suggests, we would be dealing with some gradients or slopes, and we would be descending down or going down in the direction of going in a direction pointed by our slope and trying to identify the coefficients. So our goal still remains the same, to determine the coefficients or parameters of a linear regression. So again, in the example of this temperature and pressure, we looked at that we were looking at uh, sum of square of errors, and we calculated that for n samples, this can be written as yi minus alpha xi minus beta square. Now, in case of gradient descent, we would be dealing with some differentiations. So we would say that let us define a cost function. So cost function is equal to alpha square, and we want to minimize this cost function. Now if we are minimizing this cost function, or we say that we want to minimize the average of this cost of errors that we observe over n samples. So in this case, our cost function for j's function of alpha and beta would be equal to 1 upon n yi minus alpha xi minus beta square. Now, even if we are interested in some maximization or minimization of a given expression, does not matter if we multiply or divide it by a constant, our solutions would not change. So even if we are maximizing or minimizing j, or 1 upon or divided by constant 2, we are not going to change the solutions where our particular formulation is going to attain its maximum or minimum value. And here we introduce this 2 for some mathematical convenience, which will become very clear when we will calculate some gradients. Now, the intuition behind gradient descent is that let us consider a regression model of form y equal to theta x, where theta is our parameter that we have to determine. So for a given choice of theta, we would have some error. So for example, in this case, our points were somewhere here. Now if we take this theta to be, and we are assuming that this is only slope passing through the origin, so we say that we take this theta 1, and in this case we will have some costs which would be epsilon 1, epsilon 2 corresponding to theta 1, epsilon 3 corresponding to theta 1, and so on. And then we make another choice that instead of choosing theta 1, we choose some different angle which looks something like this. So this is a pretty bad choice for parameter theta if we want to fit this. But here also we can always compute what is the loss. So this would be error from point 1 for second choice of theta, which is theta 2. And similarly here we will have some error which would be error from point 2 corresponding to theta 2, and so on. And we can calculate what is the total error that we are going to incur if we make a choice of theta 2. And we say that the average error, so in case of the choice of theta 1, our average error would be theta epsilon 1 1 square plus epsilon 2 1 square plus epsilon 3 1 square divided by total number of samples that we are observing. So we say that this is the total cost that is associated with choice of theta 1. And in case of 2, we can do the summation of epsilon 1 2 square plus epsilon 2 2 square, and so on. So that would be the cost associated with theta 2. And intuitively we should make a choice of a model where the cost is minimum. But here the craziness is, we really do not know what is the theta that we should really choose that gives us the minimal cost. One way is that we go the route of differentiation and equating it to zero and identify whether that point is maxima or minima, what we typically do in ordinary least square methods. However, when we will go to and remember, when we were talking about ordinary least square, we ended up with formulation of inverse in one case where we have to calculate xtx and its inverse. And you know that if metrics become really large, calculating inverse would be computationally prohibitive. Similarly, where we have to deal with covariance of x and y if you're talking about univariate regression, and in case of multivariate regression, we have to deal with the covariance matrix, which again is a tedious task. And that is where techniques of gradient descent, which are iterative techniques, come to a rescue. So let us try to visualize what this cost will entail. Let us say that here we have theta, and here we are and some cost is associated for each choice of theta. And if this particular function is strictly convex, and in this case we choose our cost function to be phi minus alpha xi minus beta square, which happens to be a strictly convex function. We'll not worry about convex or concave function, but all you have to remember is that a strictly convex function would be a function where there would be no local minima. If we have a minimum point, that has to be a global minima. So for this particular discussion, this much background about convex function is enough. But let us say that this is the point and this is where the choice of theta ideal is located, and we know that wherever this cost is minimum, the slope of this particular function changes, and this has to be equal to 0. Now, what we do in gradient descent, we make an arbitrary choice of theta. That is, we don't know whether theta 1 is a good choice or theta 2 is a good choice. So let us say that we start with that, okay, theta 2 should be a good value for our model. And we say that for this particular theta 2, we can always compute a cost associated with this. So, here the cost would be, if we go with this theta 2, what is the average of square of error associated with choice of theta 2. Now we know that this j theta is pretty high and we can do better. So here we are assuming some very high value of slope. So we have to reduce the value of theta. So in this case, actually we would be here. Let us say that we make a choice here, and this is theta 3, and theta 3 is some line which we assume is somewhere here, and this would be equal to theta 1. Theta 2 and theta 1 would be somewhere between theta 2 and theta 3. So one choice is that we can make a choice of theta 2. So we know that to fit these points which we have shown in cross, we have to reduce the value of theta 2, and if we make an initial choice of theta 3, we have to go towards these points. So we have to increase the value of theta 3 and go towards some function which tends to minimize the cost associated with our decision. Now we know that in case of these curves or polynomials, the fastest way to descend would be along the tangent. So what we say that if we identify the direction in which we have to move, so we say that we know the function j and we take its differentiation with respect to theta. So that gives us a direction in which we have to move, and we multiply it with some jump that we are going to make. That is, from here in this direction we will make some jump of magnitude alpha, and here we call that this alpha as learning rate. Please note that do not confuse this alpha with the coefficients of a linear regression model. That's why deliberately I've introduced this as theta, because in gradient descent, literature associated with gradient descent, alpha is typically reserved for learning rate. That is, what is the size of jump that we want to make along the direction of the steepest descent. So what we say that the new estimate of theta could be, we started with theta 3 and theta 3 minus dj or rate of change of cost with respect to theta times some learning rate. So this would be a better estimate of theta if we move along this direction with some jump of length alpha. Similarly, if we are here and here you can see that our slope is going to be positive. Hence, if slope is going to be positive, we are going to decrease the value of theta, because if this is positive, your new theta would be smaller than the previous theta. Likewise, here slope is negative. That means we are going to increase the value of theta. So similarly, we can say that for if our initial estimate is theta 2, we still say that we want to move in the direction of steepest distance multiplied by LR, and if my slope is positive, that means my theta should be decreasing, and if my slope is negative, that means my theta should be increasing, and hence we are going to try identify what is the optimal solution that is associated with our challenge. And this entire concept that we are descending in the direction of fastest gradient and trying to reach the bottom point of this particular pit, and we call this approach as the gradient descent approach. So if you want to understand the intuition, that is you are standing around in a valley, and you are on one of the mountains surrounding that valley, and you want to reach at the base of the valley. So which direction you should typically go to? You should start descending in the direction where slope is, or the rate of change of slope is maximum, so that you can reach the valley in the fastest possible way. But you're not going to fly from any hill to the bottom point, so you take small jumps to reach that point. Assuming you're taking a step of constant width, that would be your learning rate, or the rate at which you are trying to approach towards base of the valley. So with this intuition, and this intuition would be very useful when we go to deep nets, or some deep learning models that we will cover subsequently. But linear regression is one good way to visualize that. Now let us try to understand this calculations, that how this parameter is exactly updated using example of linear regression. Let us say that we want to set up a model, a generalized linear model, y is equal to theta 1 x plus theta 2, and this would be our x vector. So let me be consistent, xy vector, and this would be theta 1 and theta 2. Now let us say that we observe y1, y2 up to yn, and correspondingly we have x1, xn. So this is our predictor or independent variable, and this is our predictant or target variable or dependent variable, and we want to calculate what is the value of theta 1 and what is the value of theta 2 for the given pairs of x and y that we have observed. Now we can write cost function as square of errors, which in this case would be the ground truth of each y, of each instance of y, minus theta 1 x I minus theta 2, and square of it, since we are talking about n samples, we'll summate it from 1 to n, and since we are talking about average error, we will divide it by total number of samples that we are dealing with. And I said that for mathematical convenience, we will divide it by 2. Even if you don't divide or multiply by 2, it would be fine, but you will quickly realize why we have done that. Now let us calculate what is the direction of steepest descent along theta 1. So what we will do, we will take the differentiation of j with respect to theta 1, and we will end up with 1 upon 2n, and its derivation 2 will come out, summation I from 1 to n, xi minus theta 1 xi minus theta 2 multiply by minus xi. So this is the same differentiation that we did last time. In last lecture we equated it to 0, but here we are not going towards the analytical solution, we are going towards an iterative solution. So there is no need to equate it to 0. So this cancels out, and we end up with del j upon del theta 1 as summation 1 to n, and this can be written as f of function of xi. We can say that whenever we are saying y is equal to theta 1 x plus theta 2, y is actually a linear function of fx, and hence we can, for sake of brevity or compactness, we can write it as function of fx minus yi, and we multiply this with xi. So this is our the direction of steepest descent for theta 1 in in, a in the valley that we have been talking about. Similarly, we can write differentiation of cost function or partial derivative of cost with respect to theta 2 as and 1 by n would remain here. 1 by n summation I from 1 to n f of xi. I will leave this simple math to you. We have already done that multiple times. So this is the direction of steepest descent for theta 2. Now, again, going back to the same example, let us say this is theta 1 and we took some initial guess here. We identified this direction. So we take a jump of some magnitude alpha here along the direction of del j upon del theta 1. This is theta 1 and this is j. We can update that next value of theta 1 should be previous value of theta 1, whatever we guessed, rate of change of cost with respect to theta 1 or direction of steepest gradient multiplied by learning rate. Now, you have to think what would happen if this learning rate is too fast and if learning rate is too slow, and these are the two questions that I will ask towards end of the video. So similarly, we can write theta 2 as theta 2 minus learning rate alpha, rate of change of j with respect to theta 2. And if we have to write this in some vector or matrix notation, we can write this as theta 1, theta 2 as prior estimates of theta or previous estimates of theta 1 and theta 2 minus alpha del j upon del theta 1 del j upon del theta 2, and we will keep on updating these theta 1s and theta 2 until we converge, that is value of thetas stop changing or theta new minus theta previous if their difference is less than equal to some tolerable limit, because it may happen that that difference it keeps on changing minutely. So we can always define some tolerable limits, and if this difference is less than some tolerable limit, we say that our algorithm has converged and we will stop the iteration. Now, based on this discussion, here are the three questions that I want you to think about and work upon. And if you have any doubt, please feel free to write your comments below in our video. So three question is, can you extend this case of gradient descent to multivariate regression with k parameters? So try to write your expressions in form of final expression in form of vectors and matrices. Second question is, what happens if alpha is too large? Let us say that our learning rate is 1000 or 2000, or alpha is too small. That is, let us say that our alpha is 0.0001 or 10 to the power minus 40, some crazy small number. Third is, here is an example of some specific, let us say our x vector is specified by 1, 3, 5, 7 and y vector is 2, 4.5, 6.25 and 6.75. So corresponding to x, this is the value of y we observe. So there is one-to-one mapping from x to y. Question is, you have to fit a model y is equal to theta 1 x plus theta 2, and you decided to go with the gradient descent method. So you say that I will start with theta 1 is equal to 0.1 and theta 2 is equal to 1. So these are your initial guesses. Using gradient descent, can you update theta 1 and theta 2 using learning rate of 0.01, and after one updation, can you tell me what is the value of theta 1 and theta 2? So we will also write all the codes from scratch in Python before we go to scikit-learn, so that we develop a good intuition of the mathematics. I've been emphasizing role of mathematics time and again, because any data science course is incomplete if you are not familiar with the nitty-gritty details about these algorithms. So stick to these basics, and when it comes to the programming, you will find those concepts fairly easy if you are comfortable with this math. In next video, we will talk about Bayesian inference of linear